Welcome, everyone. My name is Elias Quinn with AcuTech, and I'll be moderating today's webinar. We'll begin with some information on the meeting platform. The navigation bar on the left includes a button to make the presentation full screen, a button to switch your audio to your phone, if that's better for you, as well as a Q&A button to submit any questions you may have, which will be answered at the end of the presentation. I see some of you have raised hands in the attendee list. You may want to check the Q&A feature, as that is how we will be taking your input, comments, and questions. So today's webinar, How Do We Improve Our PHA, is the third of AcuTech's 5-part webinar series on process safety topics. Founded in 1994, AcuTech is a global leader in process safety and security, providing management and technical consulting services, world-class training, as well as enterprise risk management software. Today's session will be led by AcuTech's PHA experts, Sam Aigen and Rich Santo. Sam began his career doing process engineering and design for ExxonMobil and has worked at AcuTech for the past 6 years, performing PSM audits, QRA, and facility siting studies, and is an experienced on-site and remote PHA facilitator for all areas of the petrochemical industry. Rich began his career in the high-hazard chemical industry with Monsanto Solutia and has worked at AcuTech for over 10 years, performing PSM audits, facility siting studies, PSM program development, and is also a certified functional safety expert with an expertise in performing spill verification. And with that introduction, I will hand it over to Sam, who will start us off with a poll.
All right, thanks, Eli. We're going to start you off with a poll here, and we're just trying to see what type of experience you guys have with PHAs. So we're asking the question, how many PHAs have you participated in? So just wanted to let you know, based on the results of the poll, it does take quite a few PHAs to really get a hang of doing them and know what you're doing and to get a better understanding of the process. And what I was trying to get at there is saying, like, you know, the PHAs can really be used even as a training tool. And a lot of times operators that are participating in PHAs really get a good benefit out of those and do use them for training. All right, so what we're trying to talk about here is risk ranking during a PHA. So there's a lot of things that come into consideration when we're trying to do a risk ranking in a PHA. We can take 2 PHA teams and look at the exact same scenario, but end up with a completely different risk ranking for the scenarios. Why does this happen? So a main driver is that there are different personal factors. You know, the PHA teams are involving people, and each different people have differing opinions. It's possible maybe that the rotating equipment engineer has different information, or knowledge, or experience, and the same goes for facilitator and team members. Possible that a team member comes from a different company or a different background or facility, and that experience is not a one-to-one comparison. And we'll talk a little bit about this later on in the presentation. Something else that I'm sure everyone has seen before, it might be possible that someone has a much stronger opinion and is just not willing to compromise. I'm sure everyone's seen that, right? So other than personal factors, there are site safety factors that can also affect the team's opinion. Does the site have a positive safety culture or a negative one? Is the PHA team are they just sitting around there and trying to convince each other that nothing bad is going to happen? Oh, it won't be that bad, not that big of a deal, probably something that you might have heard. And a key item that drives the discussion is the safety record of the plant and the operating experience. So just because, you know, you've sent liquids to a compressor and you've wrecked the compressor valves, but it didn't blow up, you know, it doesn't mean that blowing it up won't happen. It's not. It just means that it's, you know, it may be unlikely. So all of these items and others contribute to the risk ranking and will make them either be conservative or not conservative. So another thing that will impact the risk ranking of a PHA scenario is the company-wide factors. And this is the primary driver for this is the risk matrix and HAZOP procedure. The matrix could be built such that you're always tolerating higher frequencies and that you're just always in the green. You're never having any issues. And I'm sure you might have seen this before, but that's really not going to drive the right risk results. Corporate safety culture also plays a big role. So here's a quick question you can ask yourself that you can see if your HAZOP procedure is conservative or not. So do you credit a single check valve as an IPL in your layer of protection analysis? That's something to think about. The more conservative approach would be to say that you want to have a dual dissimilar check valve as an IPL and you don't credit single check valves. But if you just have that minor thing there, that can signify maybe we're a little bit more risk tolerant of a company culture. Another larger driver in developing the risk matrix is potentially that the subject matter expert for the company, and depending on if they're risk averse or risk tolerant, that could really drive, and they might be the person that's unwilling to compromise, and they might drive the risk matrix and the procedure development. Other than this, your company insurance policy, if the company is self-insured or if there's an underwriter, the insurance underwriter might drive certain, more strict risk results and risk matrices. And again, the company-wide safety record could also impact the results of a PHA. If you're in a company that has had no injuries in the past 5 years, you might end up inadvertently being more risk tolerant than a company with serious injuries recently or a fatality even. It's also possible, like we said, maybe that good safety record is just driven by luck. All right, so now we're going to do another quick poll. And I will start this poll here. So of all of the issues that we've just shown you guys, how have you seen any of these issues affect one of your PHAs? Well, if you don't mind taking a few minutes just to answering this. I know some people definitely must have seen a couple of these here. All right, getting some results in. All right, I think that's good here. So not unexpectedly here, we have team member unwilling to compromise received a very high number of votes. Another thing that we see is reliance on a site history or corporate safety history, and it hasn't happened yet. And I can't say that enough, how often that happens. Oh, well, we haven't done this, and we overfilled the tank and we had a vapor cloud, but it didn't explode, so it's not going to happen. That's just something that's very common, unfortunately, but not it's not a good thing. All right, great, thank you. Put that away. So on the next few slides, we're going to talk about several similar scenarios with varying risk rankings to show how some of these considerations can impact a team's risk ranking. All right, here we're sending bulk liquids to a compressor. And this is an inlet compressor for a midstream gas plant. So the level control valve failed close, and we're going to send liquids to that recip compressor. So sending bulk liquids to a recip is non-compressible. Fluids into a recip is just a bad day scenario. We could blow the heads off the compressor. We're going to result in a fatality here. So that drove this team to choose a B severity, which means less than 3 fatalities. They also chose a likelihood of 1 in 1,000, which is pretty likely because we only have one effective safeguard. So this site in particular had a very rich inlet gas, which means that there is a large amount of liquids. So this is a very likely scenario. But here's a question: would an operator of a facility with a very lean inlet gas with low liquids, would they have come to the same risk ranking as the site with the rich gas? All right, so here we have an identical scenario. We're talking about the level control valve failing close in front of, on the suction scrubber, failing close in front of a recip compressor. But in this scenario, the team came to the conclusion that loss of containment not expected. So at a quick glance, that's just very confusing. Why are we choosing that? But when you're doing this closer analysis, we realize that this recip compressor is on a closed loop refrigeration system. And that suction scrubber has a larger volume than the entire liquid volume of the system. So it's not likely to have a bulk liquids flow to the compressor and wrecking the compressor. So each of these scenarios, you have to have very small nuances that you have to analyze to understand what the differences are. All right, next scenario here, I'm sure we've all dealt with this before. We have a main heater valve failing open and a flame out and a reignition. And in this scenario, the team chose a jet fire coming out of the stack, and we have a result of a hospitalization or permanent disability. And the thing to note here is that this is a pretty small heater at only 1.5 million BTUs an hour, and small firebox volume also. All right. On this scenario, another fire heater flame out and reignition, and this time we're resulting in an explosion and a potential fatality. So, just one quick glance, this is the same scenario as the previous slide, but if you look at in more detail, this heater is 100 million BTU duty. It's a much larger heater, much larger firebox volume as well, so a much larger potential overpressure and impact to personnel. So if you only had experience working on a smaller fired heater, like was on the previous slide, do you think that you would identify that this larger heater has these potentially higher consequences? And then we can also think about it in the opposite way. Would it be right if you only had experience with this larger heater and you said, oh, this could end up resulting in a major incident and a fatality, then you end up driving, an advanced safety system like a BMS on the smaller heater. Is that the correct thing to do? And you can't just say, okay, this is a piece of equipment and we're always going to have this safeguard on it, because you might end up with an over-instrumented system, or the opposite way, you might end up with an under-instrumented system. So there is nuances, again, for each of these scenarios. All right, the next set of drawings, we're going to look at vessel overpressures here. This is a blow-by from an upstream slug catcher to an atmospheric vessel. And the slug catcher has an operating pressure max expected of 1,200 pounds down to the atmospheric take. So we're going to have an overpressure ratio of 1,200 times design. Then we're going to have flammable gas and liquid release, death, doom, and destruction, multiple fatalities. So there's no effective safeguard here. We just have secondary containment. So it has a very high likelihood. And the thing to note here is that this site in particular only had 2 operators, so it actually would be impossible to ever get the higher severity scenario in A severity with more than 3 fatalities. So if you only have ever worked on or done PHAs for smaller sites with few operators, it's possible that you can just get into the mindset that B is the worst, and you're never going to use this A severity. So if this was potentially on a unit inside of a refinery, we also need to think about the location of this tank. Is it located nearby a high traffic area, or is it in a remote tank farm area? So that will also impact the number of fatalities and the severity that we're choosing. All right, in this scenario, we have a similar overpressure as a blocked outlet of a compressor, a max expected overpressure ratio of 2 times design, with 300 pounds going into a 150 pound system. And so we chose a C severity, which is 3 or less hospitalizations. We have some good effective safeguards, so low likelihood. So here's a question. Would the severity be the same if the overpressure ratio was the same at 2, but the pressures were actually 1,500 and 3,000? Potentially those much higher pressures would cause a more severe consequence. Another thing to consider, maybe it was just a minor flange leak that we're thinking about, but what if the stream was toxic? We also have to consider, the toxicity and other phase parameters as well. One more overpressure scenario here. This is, again, very high pressures. We're talking about a max expected pressure of 1,200 and the design of 1040, and giving us a ratio, however, of just 1.1 times design. And the team here said lots of containment's not expected. Okay. This site in particular, we hydrotest their equipment up to 1.5 times design. And if the hydrotest was at a lower pressure, this scenario might not be accurately depicted as no loss of containment. So it's something that we constantly have to check What is the hydro test pressure? Is this a valid assumption, and potentially have to modify accordingly? All right, so what we've just seen is that similar scenarios can have very subtle differences that can create a completely different risk result. We need to identify these differences and use them as a basis for grouping these scenarios and understand those differences between them. For each type of equipment, we need to do a comparison of the upset condition versus the design condition. And then we can either make an assumption or perform an engineering analysis on how those upset conditions create holes. And then once we have a hole size, we can analyze the quantity that's released. So in most standard PHAs, the team is making an assumption for each one of these categories and then applying it to the risk matrix. It's all qualitatively. The thing we have to remember is that each time we make an assumption, we're adding some human error into this based on our opinion. And this error is compounded by further assumptions. So an improvement would be to give the team some more tools to minimize the number of assumptions that are made and minimize reliance on opinions or feelings. And now I'll hand it over to Rich, who will expand on that a little bit.
Thank you, Sam. And good afternoon or good evening to everyone. Hope you're all doing well. I'd like to talk a little bit about consistency improvements in PHAs. There are many different approaches, both qualitative and quantitative, to improve consistency across PHAs. First, the risk matrix itself needs to be verified to be acceptable when benchmarking against industry standards. Second, you want to make sure that your PHA scenarios can be grouped by common consequences or severities, and ideally identify the release sizes. If the release scenarios can be grouped by release sizes, then you can perform engineering calculations to verify the quantity released. And lastly, you can perform modeling for releases of various sizes on site-specific hazard chemical inventories. So here in front of you, what you see is a benchmark of two risk matrices that in later we'll go into further detail. And these risk matrices are overlaid on top of each other. You can kind of see the differences between the two pretty clearly. Now you can benchmark with industry standards or other companies or both, all right? The things we'll look for is ensuring that the risk matrix is appropriate for the company size. Here's an example. For smaller sites or companies to have a risk matrix with the highest severity being greater than 15 fatalities, that may not be necessarily applicable, right? Because you'll never, ever get to that particular level. When your risk matrix is biased toward the high severities, the overall risk ranking results will be lower. So the specific scenario we'll be looking at is a former company selling one of its assets to a new company. Okay, here's the new company risk matrix. Looks pretty standard. You have your consequences and frequencies and some residual risk with green, yellow, red, very red zones. Looks pretty typical, right? Nothing too much to note about it. However, when you look at the former company risk matrix, all right? When you look at the former company risk matrix, the specific thing to note is look at the new company matrix likelihood scale, right? On the former company's risk matrix, it looks like that the last two columns were omitted. So the effect of this is that the scenarios with the higher frequency of occurring are considered acceptable. If you go to the former company risk matrix and compare a single fatality, right, with a frequency of 1 in 10,000 years, the former company listed this as a risk 3, which is a very high risk, a recommendation required to reduce the risk. The new company's risk matrix has it in the green zone as a risk 1, which would be acceptable with no further risk reduction recommendations. Okay, so now that we've validated the risk matrix, we're going to propose a new risk matrix that's more conservative, right? So what we can see is the new company risk matrix as opposed to the new company's modified matrix as opposed to the former matrix. The whole matrix is shifted down and to the right, which is a bit more in line with industry standards. So benchmarking the corporate risk matrix is very important to make sure that you're aligned. And now back to Sam.
All right. Thanks, Rich. All right. So once we have the risk matrix benchmarked and we think it's in good shape, the next thing that we can do is we're going to group common consequence scenarios into a consequence severity table. So what are the potential hazards that can occur for a given type of equipment? What considerations can change the outcome from being more or less severe? As we said, process phase or composition, that'll be able to tell if the gas release, is it an explosion or is it just flammable? Is it just going to be flammable or is it also going to be toxic as well? If the release is a liquid release, is it a combustible liquid like a heavy gas oil, so it'll just have a pool fire, or is it a lighter material like gasoline or LPG making a vapor cloud? It's also possible that the material has specific concerns, like if it's LNG, it'll be cryogenic, and that'll have its own specific set of issues. So the other considerations that we also always have to take into account are metallurgy and site maintenance, and that inspection, testing, and preventative maintenance program will still determine some of the risk as well and come into play when you're developing these scenarios. All right, so here we're showing a consequence severity table for the equipment class of compressors. Then we're applying the deviations that typically affect compressors. And the deviations that we're showing here as an example are both liquids, blocked suction, and blocked discharge. So then we're identifying the differences of applying each deviation to the various types of compressors: a recip, a flooded screw, and centrifugal. And the thing we want to point out is that we're giving us a potential severity. We're proposing a severity for each of the scenarios. If we look at the liquids going to a compressor, as we said in the previous example, we could end up with blowing the heads off of the compressor, which is a line rupture, fire, explosion, and we have the B severity, which is a fatality here. And you can imagine if this happens in a more congested, maybe a refinery or a larger site, maybe this will have more than 3 fatalities. So this is just a go-by here, and you can't just blindly look at it. And another thing that we need to think about is what's the size of the compressor? Do the compressor heads, are they 2-inch heads or are they 12-inch heads? Those also will, come into play in the quantity that's released. All right, so now we're doing the same thing, and we're looking at piping and vessels, and we're applying the deviations of pressure and temperature. We take a look at the pressure deviation at the top. We can see that the overpressure is categorized, and I'm sure you've seen this before. This is a very common thing to do. And we're providing a sample severity level for each category, where we have the highest resulting in 1 or more fatalities, and the lowest category does not expect the loss of containment. So once again, we have to apply the site specifics, and the site in question, if the site in question performs their hydro test at a pressure less than 1.5 times design, like is shown on this table, the categories will need to be modified accordingly. So another thing I wanted to note is the severity column. So what are we really doing in this column? We're really answering the question of how much material is being released. And this is an assumption. We're assuming how much is released, and we're saying this is how bad it's going to be. But I want to note that a more quantitative approach would be more accurate and leave less to question, and Rich is going to expand a little bit on the release quantity.
Thanks, Sam. In an ideal world, we would take every scenario identified in a PHA, perform a quantitative risk assessment, or QRA, on the scenarios to accurately determine the real individual and societal risks to the site. However, that would be very time-consuming and prohibitively expensive. But what we can do is minimize dependence on assumption or opinion by performing detailed calculations in a generic manner and providing the PHA team with something more quantifiable, all right? So first, we can use group experience and assumptions or industry databases to agree on or calculate a hole size for a given scenario. For example, if you have a heat exchanger leak or a leak to atmosphere for a corroded tank, the team can agree on a hole size, for example. Now, once that's done, a series of modeling can be performed to identify the release quantity over a given time period for various hole sizes at various pressures, right? So what you see in front of you is a simple nomograph, right, that lists different common hole sizes and different release pressures with different release quantities. And you can find this nomograph in what formerly was the crane manual and different other resources. For example, we can follow the line for a 1/4 inch equivalent hole at 300 psig, and we can find a release quantity from that. We follow the graph, right? Okay, another thing we can do is to perform site-specific dispersion modeling to generate a consequence severity versus release quantity for the chemicals of interest. Okay, here, this is an actual example of a site-specific consequence severity table, which was developed using the conceptual table in the CCPS LOPA book, 2001 version, as a guide, right? So what you do is you can take the various chemicals and flammables, combustibles, toxics, etc., of interest in your particular site and perform dispersion modeling, right, using various release quantities. In this particular instance, DNV's FAST, or Process Hazard Analysis software tool, was used to perform the modeling, right? Now, based on the results of the modeling and the release quantities, we can target a value of the consequence levels to each of the consequence levels in the site's risk matrix and enter it into the table. So that way, the PHA team has in front of them a well-defined and a sound basis for consequence severity from which to select from each range of their release quantities. So it reduces or eliminates inconsistencies in defining the consequences, and it improves the efficiency in the PHA. Right? Okay, now we're going to have our third poll, and we're going to ask, what pieces of this webinar have been used in the PHA? Okay, some results are coming in. All right, it looks like based on the information coming in, the percentages are still holding that consequence severity tables and risk matrix benchmarking are the two largest tools that have been used. This is good. This is good. At least this shows that folks out there are using tools such as this to improve their consistency.
And I just want to point out, Rich, also that the release quantification tables is the least used, and that could be something that's very beneficial in in making the results more accurate. All right, we'll go back.
Thank you, Sam. Okay, to summarize, we've discussed how PHA teams typically function, using in large part group opinion and consensus to quantify the severity and likelihood of potential incidents. There are various approaches that can be taken to help improve the consistency and accuracy of these analyses, right? They include having a risk matrix that's benchmarked against industry standards, having a list of consequence severity descriptions for various equipment failure scenarios, and developing a site-specific Consequence-Severity Table using dispersion modeling software. So when a PHA team leaves less to group opinion and leans more on these types of tools, risks are more accurately identified in less time. Not only improves your efficiency, but what this allows you to do is to consistently apply your risk analysis across not only your site, but all sites in an organization.
Thank you very much, Sam and Rich. Apologies for earlier. I can hear you both perfectly now. So, with my hearing restored, we can take some questions. I haven't seen many come in, but we do have a few excellent ones in the Q&A. And since the consequence severity tables came up so highly in that last poll, how about we start with a question concerning whether or not consequence severity tables can create a potential risk of stymieing or preventing constructive feedback and discussion during PHAs.
I guess I'll take that one. So I think that using the consequence severity table, it should just be used as a basis, and it's a good starting point. And I think it really does help save time to get people in the mindset of, okay, is this scenario going to be in the area of a fatality, or is it going to be less than that? And it should be reiterated though that this is just a starting point, and you really need to reinforce that we still need to take all the specifics of the given scenario into account, and before we're doing the risk ranking for that scenario.
Thank you.
Yeah.
Going in order that the poll indicated interest in, how do we know if a risk matrix is good or not? And what goes into benchmarking a risk matrix?
I can take that one, Eli. There are multiple sources for benchmarking risk matrices. You can use, for example, there's information from CCPS, which is the Center for Chemical Process Safety. And one of the most important things when looking at the risk matrix is looking at different levels of, you can look at it in simplistically, looking in terms of levels of severity and injury and seeing if they make sense in terms of matching what would be an acceptable risk. For example, previously in industry, this is changing. Typically, a facility would accept a single fatality at a frequency of no more than 1 in 10,000. So 1 times 10 to the minus 4th. This is now becoming a little more conservative, where you'll see the acceptable range for a single fatality moving towards more of the midpoint, 1 times 10 to the minus 5th, something like 5 times 10 to the minus 5 or a little bit smaller. So this is a good indication. It's one pivot point of your matrix that you can check. If you see a risk matrix where a single fatality, for example, is down in the example that we showed, somewhere around the 1 times 10 to the minus 3 range or more frequent, you know right there that the matrix is not being conservative enough, and you could potentially misrank scenarios that sorely needed additional safeguards, and you would have accepted those risks.
Thank you. Follow-on question on that same topic. We have somebody asking about determining the environmental element of the risk matrix, and I think the desired outcome for this question is probably to see if there's any best practice or guidance that can be referred to, any overarching regulations that define it. You know, where do you go to see what the best practice on that column of a risk matrix would be? in the environmental context.
Rich, you want to take that, or you want to?
Yes, no, I'll take that one as well. That's a great question, because the environmental column is much more subject to local conditions than are the injuries. Basically, an injury is an injury. If you're going to get a chemical on you in one state, it's going to be pretty much, or location, it's going to be pretty much the same results as it is in another. However, environmental impact can be different in terms of your site topography. Whether you're in an area that has soil that is subject to a lot of groundwater contamination or not. You may have a state that has very stringent air emission regulations in which small releases are reportable versus non-reportable, or that spurious releases, for example, of relief devices or flaring events are reportable versus not reportable. So it's very, very site specific when you look at the environmental column, and there is some subjectivity to it. You know, it's a little less concrete than simply looking at the personnel safety severity table. Go ahead, Sam.
I was going to just expand on that a little bit. That I think that when you're doing an environmental risk ranking, most often in many consequence tables for many companies, the environmental column is really driven by these major oil spills, like in something like Macondo in the Gulf of Mexico. But a lot of the times in most PHA scenarios, we're talking about a minor air emission, and there's not very good descriptions that are just defining these smaller magnitude releases. And I do think it's doing the study a disservice to make everything a low-level environmental 1, for example, whatever the lowest consequence severity. And I do think that this is like a good room, an area for improvement when you're trying to improve the definition of your risk matrix, for example.
Thank you, Sam and Rich. I've also seen this challenge in many places, and it's obviously the hardest one to fine-tune depending on where you are in the world or what your site is. So that is an excellent question. Segueing from the example you just gave, Sam, where very often these can look at larger oil spills and kind of be inspired by those and trying to put the matrix together for better or worse. A lot of the examples that we provided are from midstream. How is this applicable to downstream?
I guess I'll take that one, unless you want, Rich. I think we're talking about the consequence severity tables, and I think all of this is really applicable to anything, any industry, not only midstream or downstream. It could also be upstream. It could be chemical, petrochemical, pharmaceutical. For each niche industry, you could have your own tables. And if the question is about downstream, maybe instead of having it by grouping types of equipment, maybe it'll make more sense to go by unit, and you can have a consequence severity table for each unit. If let's say you're a major oil company, and it would make sense to have these consequence severity tables, and you'd say, this is my table for the FCC, and then you can maybe take a look at what one FCC versus another FCC should look like, and different typical scenarios and high hazard scenarios, safeguards, and things like that.
Okay. And just to give one more example, because we had some follow-on questions while you guys were talking about the environmental side before we move on. Are there key points or criteria that you use, such as, is it all based on costs, permit violations? I believe the person that asked this question is likely US-based, just from the language of it, and talking about either state or EPA permitting. So is the cost criteria, or is the cost administrative or bureaucratic?
I can answer that one, Eli. Yes, the answer is yes. Typically, what you see is the costs in your definitions of the various environmental consequence severity levels include all of it. It can include, the costs for cleanup. It can include fines or permit violations. It can include costs that potential lost business from, bad publicity from a large spill, etc. And that's all part of constructing that risk matrix. And again, the environmental column, if you will, is one of the most difficult to do. But I think of it when I have done this before for other folks. You have to almost think in terms of defining at each level what the site would consider something minor or moderate or major or catastrophic, and that may vary company to company.
For example, enterprise level 1 could have very clear 1 through 5, and you may be at a site that can only generate a 3. This is one of the things we've seen, and one thing that I know we've cautioned on many individual bases to be cognizant of, that perhaps your worst day is not the 5, it is the 3 or the 4, but another site in your enterprise could be the 5. So that's also something handy to consider.
And Eli, I also wanted to add something. I think that you could potentially break those two things. If it's between costs and permit violations, you can break those two out into 2 separate columns, and that could be a better way to do it. So in your consequence tables, instead of just environmental, where you have everything lumped together, the environmental, permit violation, fine, etc., you might have the financial, the actual impact to the environment, and permits as separate line items, as well as for community impact or PR impact as well.
Yeah, that would be very useful. And the only thing to remember there is not to double count, not to count your financial twice, capturing it once in environmental and another time in financial. But I think a lot of us feel that having multiple layers of data to examine is better than not. To switch gears a little bit, we have a question about the release quantity and how to develop a release quantity table or graph like the one we showed.
Sure. Be glad to answer that. For example, the example that we used is based on the it's a example, and it's completely qualitative, essentially, from the CCPS LOPA Layers of Protection Analysis book. And that table, what it showed was a listing of particular substances, and it gave ranges of release quantities. And then in the table, what it showed was an example where it might be at different levels what consequence severity would match up with that particular site's risk matrix. But that is completely theoretical. What you have to do to be able to use that is you have to develop that table for your own site. So, for example, if you were going to do this at a site, you would list all the chemicals and substances of consequence, all the things that if they were released would either result in a fire, explosion, toxic release, etc. You would try to quantify the ranges that made sense for the size of your site. So, you could be in ranges, if you're very toxic, less than 1 pound may be a quantity that you would look at. Typically, you might do something like 1 in 10, 10 to 100, 100 to 1,000, etc. And, you'd cut it off at the level at which it made sense for your particular site. Then you can model those releases You can take a midpoint of the ranges. You could take a few points in that range and average them. You can take a geometric mean of the range, etc. And you can perform release scenarios, do the dispersion modeling on those release scenarios. So, for example, if you have a release of, let's say, something like butane at 10,000 to 100,000 pounds, you can model a 30, 40,000 pound release, the midpoint of that range. You can model it in FAST or another software tool, look at the dispersion, what you're likely to get in terms of a flash fire or a vapor cloud explosion, etc., and then make an estimation for your site, given where that material may be released, as what you are likely to get in terms of a consequence severity. So, for example, if you have that chemical of interest, for example, next to a control room, that if you had a fire or explosion of that quantity, maybe you would have, say, the potential for multiple fatalities. You would then look on your risk matrix to see where multiple fatalities would fall, and then that's what would be entered in that particular part of the table. It might, depending on the risk matrix, it might be a consequence level 5 or 4 or what have you. And you basically go through the entire table, plugging in these values. And once you construct this table, then what you have is, for site-specific releases, you can determine what the consequence severity is.
All right, thank you. And one other question that I think is in similar spirit there. What about the consideration of MAWP for consequences? And how would that, how is that significant?
I think I can take that one, Eli. So this is an interesting question. So when we're doing a PHA scenario, we have to take into account what the design pressure is to identify where we're going to potentially lose containment. But there is, when I was showing the consequence, the overpressure tables, and the lowest one of, if we're saying that we can overpressure up to the hydrotest pressure, well, we've proven that we can exceed the design pressure a little bit and not have any releases. So that's the reason why we're saying that we can exceed the design pressure but not expect any release. Now, according to code, API 521 for pressure vessels and API 2000 for atmospheric or low pressure storage, you still need to have overpressure protection, and that has to be set at the design conditions for the equipment. So this is a place where the code and the PHA methodology actually disagree, and the PHA is actually less conservative than the code. The code says you shall not allow yourself to exceed the design pressure of the equipment, but the PHA says, in reality, we're probably not going to have a release in that event if it's just a minor overpressure.
Mm-hmm. If I could expand on that a bit, Sam, some sites have chosen, that we've worked with, some sites have chosen to actually recognize this fact. And for example, then they would rank that particular scenario as no loss of containment expected, potential exceedance of a design limit. And that then would have a particular consequence severity assigned to it. And that way you recognize that, you're not going to likely have a release if you take the tank or take the piping at 32% over maximum allowable working pressure, but you're above a design limit. You're not supposed to do that. It's a potential, you've exceeded a design limit. So you're going to recognize that.
Thank you. So that's actually all of the questions we've received. I think several of those were excellent, and I really appreciate the audience participating and giving us those questions. So that, I believe, will be our webinar. That is all of our questions, and we will wrap up. We do hope to see all of you again at our webinar on September 8th. That will be about the importance of inherently safe design studies. In the meantime, you may direct any questions you have or requests for how AcuTech can assist you to info@acutechconsulting.com with a hyphen between AcuTech and consulting. And I just want to take the opportunity to thank both Sam and Rich, and most of all, thank all of you for joining us. And we all hope that you have an excellent afternoon or evening or morning, depending on where you're tuning in from. Thank you so much.
Thanks, everyone.